Okay, I'm going to be doing problem number 1 of Unit 5. The problem is a circular dielectric disk has a uniform surface charge density of 1 microcoulomb per meter squared. If the disk has a radius of 10 centimeters, at what angular speed must the disk be rotated to produce a current of 50 nanoamps across a straight line extending from the center of the disk to the rim? So I think the hardest part about this problem is figuring out what they're asking. So this is what the diagram will look like. This is your disk. It'll be rotating like so, and this is the line at which you want to find the angular speed. So to find the angular speed, you'll have to go through finding the charge that goes through it and then comparing that to the current that they give you. So they said in the problem that the charge density is 1 microcoulomb per meter squared. And that we're just going to represent as sigma because it's the density of the plate or disk that's turning. And to find the charge that is going to go through this line, we have to find the area of the disk, which is pi r squared, and your r they give you as 10 centimeters, so we change that to 0.1 meters squared. And then that's going to give you 0.0314 meters squared. Okay, and then to find the charge, we just multiply that area times sigma, so that's 1 microcoulomb meter squared times 0.01 pi meter squared, which you found up here. You can use 0.0314, this is just more accurate, but it doesn't really matter. So that's just 0.01 pi microcoulombs. And then this is the amount of charge that passes through the line every revolution, or 2 pi radians. So again, just looking at this diagram, they want to find the angular speed of the disk through this line, and to find that you have to have the charge that passes through the line every revolution. So that's what we just found. Okay, and going on to the next part, to find the number of revolutions per second, you have to use the equation given of I equals NE over T, where T is 1 second, because they say it takes 1 second for the disk to complete a full revolution. Then you're going to equate that equation with the value of I that they gave you of 50 nanoamps, like so. And for E, you just plug in the charge that you found previously, the charge on the disk. And then you're going to solve that for the number of revolutions needed, or N as I used, and that's going to give you 10 radians per second. So it's just this 50 divided by the charge, which is 5 revolutions per second, and then you have to convert it to radians per second, so the revolutions actually cancel out. Ooh, this pen. Revolutions, and then it gives you 10 radians per second.